Welcome to the lecture 6 of the optimization course. In this lecture, we will first deal with an algorithm which is known as golden section method, which is an optimization method that can be used for solving one variable optimization problem. And the reason we are going through one variable optimization problem is we want to gain intuition behind how optimization algorithms work. In the last lecture, we talked about various bounding algorithms that bounds the range in which an optimization solution lies. And once the bounding has been done, then you can use an algorithm like a golden section algorithm to find an optimal solution. And that is the focus of today's class. So the first thing that I want to do in this class is cover the concepts which are related to the golden section method. For example, what is the golden section ratio, where the idea is coming from, and then give you some intuitive background about how the algorithm works, and also showcase you an example problems where we are using the golden section algorithm. So let's get started. The first thing that I want to do is I want to talk about some of the basic derivations that are typically used in golden section algorithm. So if you recall, if you have a function, let's say, this is one variable problem, so we have x-axis and this axis will be fx, right? And we have a function which is depicted by this yellow line, and maybe hopefully through using a bounding algorithm like Swan's method, we have bounded the bound of this function by a and b. This is something that we have determined. And the way this algorithm works is basically within this lower bound a and upper bound b, this algorithm always keeps tracks of two solutions in between, which is known as x1 and x2. Okay, and it iteratively changes the values of this x1 and x2 in such a fashion that we converge to the final solution, which would be somewhere close to this point in the overall optimization. So this is an optimal point for this overall function that is here, and that's what we want to find. And you will see this iterative method which is using this golden section approach to locate here. Now the idea of the golden section method comes from golden ratio, and let's see how this golden ratio is typically used in this optimization algorithm. Okay, so again we position 2 points between the interval, and then typically x1 is at tau. So the way we do this x1, this x1 is located from the tau of the right end. Okay, and similarly the x2 is located from the tau distance from the lower bound. Okay, so the x1, this one is located from the tau ratio from b. The x2, which is here, is located from the tau ratio from a. So you can see this tau and this tau, these are same, and correspondingly, if you assume that this whole interval is 1, then this will be 1 minus tau. Let's see how we can use this tau value, and let's find out what is a good tau value to use this convergence approach. And this idea comes from basically the golden section algorithm. So if we have this function, right? Okay, if you look into this two function evaluations that you have probably done, so if we have x1 and x2 here, and we have done some function evaluation, so here we have done fx1, which is one function evaluation, and at x2 we have done a function evaluation fx2. Right. So in this case, if I compare fx1 by fx2 value is going to be lower than fx1, and that means that the solution probably lies in this region, because the solution values is decreasing, and we are most of the cases interested in finding the minima. So that's why we know that the function value is decreasing in this direction. So it will be a good idea to basically block out this region, and we can block out this region, and then we can focus our search now from x1 to b. Okay, and now what this search algorithm will do is it will make x1 a, b will be b, there will be x2, and it will again sample for a new point which will give a new value of x1 and x2, and that's how it iteratively works. But the intuitive thing that I want you to take away from this diagram is in this iteration we basically want to block out this region and we want to focus on this region, because we know because of the comparison of this function that this is not where the solution lies and this is where the solution lies, right? So what we will do is we will use this idea of basically reducing the interval. So we initially we have this interval, and after blocking out we will have this smaller interval, let's call that I dash. We will be shrinking this interval and we will be moving in the right direction depending upon these function evaluations that we have. So let's see what is a good value of tau to use in this algorithm in general, and that is where the name golden section comes from. Okay. So let me erase what I have here and then quickly show you how the golden section ratio or derivation comes into picture. Okay. So if you look into this diagram, right, what we have done, similar to what I illustrated, right, we knew that we have x1 and x2 values, and since fx2, which is the function evaluation of this function at x2, and fx1, which is the function evaluation of x at 1, is here, and we know that fx2, which is this point, is lower in value than fx1, we need to block out this region and we need to move in this region. Okay, so let's assume that before we did the blocking out, our original interval, which is marked by this arrows right here, which is between A and B, so B is right here and then we have A right here. Let's say this interval was I. Okay, now we blocked this interval, and then now our new interval becomes between x1 and b, and let's call that interval, which is denoted by this red line, as I dash. So right here to right here, let's call that I dash. Okay. Now what we need to do is we can use the relationship or the idea of this ratios that was given to us before, and we can find out what would be a good value of tau to use in this overall algorithm. Okay. So we know that x1 is tau from the right hand side of it, right? And we also know that x2 is tau from the left hand side. So this all relationship is known, and then we need to find out a good move in the next iteration, right? So if we do that for the efficiency purposes, for getting more efficient result or faster convergence over the overall search process or bracketing process, or basically interval reduction process that I showed you, it will be good that after eliminating the left interval, the x2 needs to be tau of the new interval that we have. Okay, so recall what we showed is, in the previous diagram, we showed that this interval right here between this and this was I, right? And the new interval, which is marked by, in this diagram, marked by this blue arrows, right here, is essentially I dash. So from there, we can draw some conclusions and we can create some equation that might give us an intuition about what is a good value of tau. Okay. So one of the things that we can do is we can compare the distance between x2 and b in I and I dash. So if you look into this distance bx2, right, that is equal to 1 minus tau times I. So that's what we have written here. So here what I'm doing is I'm focusing on this distance bx2, and I know that that is equal to 1 minus tau times I in the interval I. Now if I take the new interval I dash, in that new interval basically what we have is bx2, since I said that the new location has to be the location that I have now here in this one, right? This has to be tau times this interval I, right? So the distance bx2 in the interval I dash has to be tau times I. If we have that, then we have an algorithm that is going to be converging fast. So that's one relationship. So this is something that we can call the first relationship between the interval I and I dash as we are iterating through is happening. And the second equation that we can write is basically relating I and I dash itself. And we know that what happens that I dash, right, is tau times I, right? So this distance was tau, or this x1 was tau I1, right? And that is the new interval that we have, which is I dash. So tau times I is equal to I dash, and that is something that we can write here. So this gives me a second equation right here. So this becomes my equation 2. And when I combine both of these equations, right, we have this equation which is 1 minus tau times I is equal to tau times tau I. And what I've done is I have substituted this I dash, which is equal to tau times I, right here. Okay, so I took this tau times I and I just put that in place of I dash in equation 1, and that is how I am defining this equation 3. So the equation 3 is essentially combining equation 1 and 2, and then we get this equation. Now what we can do is we can solve this equation and we can find out what would be a good value of tau itself. So let's go ahead and try to solve this equation. So if I move forward, right, in the next slide, from the equations that we have previously, what we can do is we can write this overall equation, which is 1 minus tau is equal to tau times tau. I have basically cancelled out, I and I from the previous equation 3 that I have shown previously. And then from there I get this equation, which is tau square plus tau minus 1 is equal to 0. And then that's the quadratic equation, so I can solve for it, and essentially I will get this ratio, which is 0.618. So this ratio is essentially known as golden ratio, right? And this is where the name for golden section approach comes from. This tau value of 0.618 is called a golden ratio, and this is what we are going to be using in our overall algorithm. And the connection of this is also with, a well-known, thing in mathematics, which is known as Fibonacci sequences. If you have Fibonacci sequences, then the ratio of fn by fn minus 1, that tends to 1.61 by 1.618. And if you take 1 divided by 1.68, that is equal to 0.618, and that is also known as a golden ratio in the Fibonacci sequence. And since we have a tau value of 0.618, this overall algorithm is known as golden search algorithm. So this is where you will see the tau value of 0.618 is coming into picture in the algorithm that I am going to talk about. Okay, so with that, what we will do is we will move on to the next part, where I will give you some intuition of how the overall golden section algorithm works.